I'll be easy on you. So this is going to be interesting. So I have a much simpler talk on RT flow and some of the applications. So now that we're done with the advanced stuff, so you can ask me the questions. And this was intended to be for an intermediate audience. So hopefully, if you have heard RT flow before, but you didn't use it, or you don't know maybe how applications might use it, and some parts will be easier because we've already covered some of the applications in the prior talk. So my name is Mesut. I work for Intel Labs as a research scientist. So, and this will be the introduction to the flow offloads. So it's, as you can tell, it's a popular topic. So you've heard 1 and 2 this day, and tomorrow there will be more. But the fact is, offloads are nothing new. So some of them we've seen every day, so we kind of like drive past them. So it probably started with getting some basic frame CRC out of the NIC. So can I convince anyone to do software CRC checks for your frames today using CPUs? Probably not, right? So, and then it basically moved on to maybe some scattered gather offloads for DMA operations, and then checksums started to appear and then started going up in the stack for higher layer protocols. And we all take granted RSS hashes that are conveniently supplied by those NICs. So these are all means of offload. And then segment offloads are also useful things for transport layer protocols. GSOs, GROs, TSOs of the world, they all appear there. And I just took a random NIC on a random server the other day and just printed out the offloads. They're not visible, but it's a long list. So any NIC you take out, just try to dump out the offloads that it supplies today. It'll be a long list. So we do benefit. And then one of the, increasing availability happens to be on the side of, matching packets to flows as well. So, and then there are interfaces showing up for people to use these. So you can go ahead and use some of the, primary tooling for going and programming some end tuples for your, Ethernet hardware. Something like Flow Director for the case of Intel. Or you could be using maybe some of the offloads available from the kernel infrastructure using TC Flower. And then last but not least, DPDK gives you a nice API for basically programming some of these rules to hardware and get some assistance from it. So I'm not trying to draw a very rosy picture of this because it's an area of active development, like you've heard. I mean, we've talked about some of the action parodies and some of the enumeration stuff. So how do you really know whether that piece of hardware is really supporting what you're looking for is another area. So hopefully there will be towards the end some opportunity for discussing these. So I'll get back to those. So the regular programming goes by telling you the introduction to RT flow. So it basically lets you match packets, incoming packets, to certain rules. And it might be the part of the packet where you have the protocol headers or payload, or it could be actually about the metadata. So which port this came in from, whether that's a physical function X or a virtual function Y, or a port representative for that matter. Keep in mind that these features, all of them may not be present in a particular hardware implementation of that API, but this RT flow API first appeared a number of years back. And then the general lay of the land for application using it is as follows. So the application would come in and then use RT flow API to put in some rules into the hardware without really caring about what exact hardware it is in theory. And then the POMO driver implemented for that hardware would really go in and then convert those API calls into a form and shape that piece of hardware really can understand. And flow rules themselves are the things that the PMD will be installing onto their own devices. And as you install these rules, you will get an opaque handle in return. That'll be handy when you need to really use those things for updating them, getting some statistics out of them, or deleting for that matter. And a rule is a combination of those three things. It would be the flow attributes, a set of matching patterns, and then a list of actions related to it. So let's take a look at the parts that constitute those three areas. So the flow attributes will be residing in a flow attribute data structure. It might be talking about groups, so you can actually put those rules into logical groups. And if you're coming from an open flow world, they're called tables. And then if you don't do anything, things will be going into a table, a default table 0 or group 0. So if you're trying to jump tables like you've seen in the earlier talk, you would be probably grouping them into different numbers and then jumping along them. And then you could also specify whether this particular flow rule should be applied for those packets coming into the NIC or the ones that you're trying to transmit out of the NIC. So how do you really match a pattern? So how do you specify those packets pertaining to that particular flow? You use one or more of those items showing up in RT flow item. And the thing about it is if you have been using a certain protocol, you need to make sure those items are appearing in the order that they are appearing in the form of protocols. So you have to basically match the stacking of the protocols as you're trying to match them. But once you do that, you have an option to specify the value that you're trying to match on. It could be an exact value, or it could be a range specified by that last value. And you could also use masks to bit mask some of the value or the range. So you could specify kind of like a wildcard rule. So, and the last part is basically the actions. So the actions would be, one or multiple. And you can, count packets, drop them in cap, decap, and then you've seen some of the actions covered earlier on as well. And you can queue them up to a particular queue or calculate RSS hashes on it, etc. So, and then this is a quick look at if you were to use the API and program those, combinations. On the left side, we're just trying to create a simple rule with group 0, no priorities involved. So priorities actually help hardware resolve the overlapping rules. So basically, if you have 2 rules that might be applied to a given packet, and if you did not specify any priority for it, you might be in trouble. So the RT flow behavior would be, here in this case, undefined. So hardware may reject your rule, or it might just apply arbitrary one of them. So, and then we're saying this should be an ingress rule applied to the incoming packets. And then here on that middle block, we just created an Ethernet matching flow item. We just grabbed an RT flow item object. We just added some Ethernet specification saying that all 0 addresses should be there with a mask of all 1s, and then basically added to the list of items. And then on the action side, we chose to use an action called mark that basically takes that arbitrary ID, and whenever you see the pattern matching that in that middle block, you would be putting that mark, that arbitrary ID, into the packet's metadata. So in the particular implementations, this will likely transfer through that PCI bus, through that hardware descriptor, and your PMD would probably be translating that into your MBUF structure. So the API's calls for management. So it's quite simple. So we have, and the ones that do not show up on the screen, I'll talk about those. So the first one is about validation of the rule. Unfortunately, you cannot come in and then query a device, from get-go saying, okay, tell me what are the things you support, and and I'll craft my rules according to that. We don't have that capability in this API yet. So you basically have to form your, rule and then try to validate it with the driver using the flow validation API. And then the difference between validate and create is you actually do the action of installing the rule into the hardware on the create. And some of the actions require data to be stored as a state for that flow. For example, if you're trying to count the number of packets or bytes in a certain flow, you would later come in and then read the current value for that counter. That would be given to you by flow query. And then the one that got concatenated at the end is destroying the rules and also, flushing all of the rules associated to a given port. So applications would be using the opaque rule handles as a reference to those rules, and the port ID that was referenced in all these APIs gets somewhat magically converted to the underlying ETH device that we're operating on. So the application spotlight here is Open vSwitch. So it's a software vSwitch application. For those who are not familiar, it is actually a predominant vSwitching application that you can find in a lot of places in the cloud as well. And then obviously, in this conference, we're talking about the DPDK user data plane for Open vSwitch and how it would be using the RTFlow API to facilitate some of the offloads it cares about. But before going in there, this is the very simple OVS overview for you. So you would have a network device, and OVS would be on the DPDK user data plane, would be using a pull mode driver to pull packets out of that device. And RTFlow driver implementation would be part of that PMD. And then it would go through three basic stages here, some pre-processing on that packet, trying to make sure that it is ready and efficient for memory to actually further process that packet in the switching pipeline. The lookup would be the main heart of the pipeline, that you actually find a matching rule, and then you find out the action and try to carry that. So OVS is implementing a standard OpenFlow switch. So somebody like a network controller or an orchestrator or a mere mortal with a terminal screen would come in and program some OpenFlow rules. And as you basically look up this packet, you're supposed to resolve those rules from those OpenFlow tables and try to apply them for that packet coming in. And the hardware offload feature for OVS appeared relatively recently. So it was about last year. It's still an experimental feature. So you would come in and then set the hardware offload flag for that OVS. As you can see, it's like a large hammer. You just turn it on and then hope that it works. So it's not a very finesse thing yet. But what it supports is so-called partial offloading. I will come back to that notion of partial offloading, but it simply says that you try to get some acceleration out of your NIC by using offload concept here, but the action and I/O part of the pipeline is still carried out by the software switch. And this allows OVS to skip some of the costly operations that are listed here, and maybe next slide I can talk more about those things. But the protocols it would support are shown underneath there. So if you have a rule that really does not match any of those protocols, it is more advanced than that, at this point in time, you're out of luck. So, and then the OVS pipeline shown on that figure is kind of like the expanded version of the figure I showed in the previous slide. So those three stages are now shown in 4. So the first one is that pre-processing stage where you kind of like compress the data structure to make it more efficient. And then the remaining ones are 2 cache stages. So OpenFlow protocol classifier is at the end. So once you resolve the flow, you just don't only take the action, but also install some breadcrumbs along the way so that next time you see packets pertaining to that flow, you can actually do this job faster so you don't have to go to the full protocol processing again. So these caches are important. And then the first cache, which is an exact match cache or a signature match cache, allows you to do this thing called the so-called fast path, so you can locate the flow easily. And with hardware offload feature, this will basically, whenever you install some caching information into the data path classifier, it would go back and tell the NIC saying, hey, by the way, if you see these packets again in the future, can you please mark them with this XYZ value, which is an arbitrary ID, but it is unique to that rule, so that it could be later referenced to find that flow, and that would give you a faster path. So zooming into, it'll be fun. So the area that you see as white has actually a description of what exactly it does, and I'm going to describe it to you verbally. So the first thing it would do is when it tries to install a cache into the Megaflow entry, it would basically come up with a unique ID for that flow that was not used before, and then use RTFlow's create API to install that rule into the hardware. The work begins actually on that critical upcall path where you try to resolve the flow, but we don't actually do the installation of the rule right away. We basically defer it to a service thread because, as most things in life, it takes time to install rules. So we kind of like make sure that we resolve the flow, do the action right away, but later come back when that main data processing thread yields, we can come back and install that rule later on. So we talked about priorities and overlapping rules. One good thing about this particular application's use of RTFlow is that it actually does all the legwork to make sure these cached flows are not really overlapping. So it makes the use of RT flow quite easy there, so you don't have to deal with the priorities. And OVS does not really have a lot of advanced features in terms of trying to remember things that did not get offloaded because the hardware did not support. So the flows have certain limited timeout, and then after that, everything starts from scratch. It would relentlessly try to offload them again. So this is the only slide where you will have a lot more vendor-specific information. This area happens to be where we contributed to DPDK last, so bear with me. So Intel's 700 series adapters are quite prevalent, so you might probably find it any recent server. And we have supported RT flow feature with that PMD, I4TE in DPDK since the API's inception. And internally, it does use flow director feature for certain protocols to implement those flow features of RT flow. And it is supporting those actions shown. And it does allow you to install up to 8,000 rules into the device memory. So what we have added more recently in DPDK 1908 is the support for mark and RSS actions together. And those two happen to be the actions that OVS chose to use in order to get the flow rules installed to the hardware so that it can actually accelerate this pipeline. And then later on for this 1911 version, we have actually added the support for flow director in our vector receive path. So vector receive paths for RPMDs happen to be the default ones chosen on most of the recent hardware. So if you were to basically download OVS and DPDK today, in likelihood, this will be the path taken. So we've added flow director. Thus, with those two things, we can actually support hardware offloads for OVS. You can try it on the DPDK next branch now, or you can wait until the next time OVS uses an LTS of DPDK in March next year. And then there's some link here for you to take a look at the details. And if you're interested in RT flow's performance in more detail, come back tomorrow morning. Chenmin, somewhere here. There you go. We'll come back to this stage and talk to you about some of the optimizations he worked on and put into the RT Flow API implementation for our NIC. Okay, so I'll show you some test results and hopefully then go into some of the discussion. So we've done some tests, but I've shown here two basic ones. A phi-to-phi test on the left side where we take a traffic generator, we take two ports of our NIC, and then simply use OVS DPDK to take packets from one and forward it to the other port. So that's called the phi-to-phi test. And we do pretty much the same thing on the right side, but this time we also spin a VM. It has its own virtual ports based on Vertio here in this case. And we would do the same forwarding all the way up in the VM just to come back out with the same packets out of the port. So, and then we look at the performance of various different sizes of packets and different number of flows and rules. And flows and rules are also a concept that is somewhat abused in terms of terminology. So when I talk about flows in the experiment results, I actually refer to those things that travel in the wire in the form of 5 tuples, different one of those. And then the rules are the things that get installed into table to govern those packets, right? So I'm not going to go through every single one of these things, but I just want to show maybe like 3 trends here. So just to match the visual on the prior slide, on the left side are phi-to-phi tests, on the right side are the phi VM phi tests. One thing that seems to be happening here is the benefits from turning on the hardware offload for this particular application seems to be quite consistent and independent of the packet size, except for those 1K packets where you actually reach the line rate for that particular experiment. So another trend is as you install more rules, and especially the particular numbers we chose for this is we try to make sure we actually exceed the capacity of the underlying NIC to see how it really starts to behave. So obviously you see a graceful degradation as you have more rules and some of the rules don't fit. And I'll come back and talk about these things. This is a real problem. And in general, you will always have limited hardware and then probably more flow rules to install than that particular hardware. So what do we do? And the third trend I wanted to show you here is, as you do more with that CPU, so by the way, these are single core numbers. So you basically take that single core, run those 2 ports along with those verti interfaces, along with the VM, and then see how the performance looks like. And as you do more things with that CPU, obviously, there are less cycles left to get those packets from the hardware, thus the benefit of really getting the offload, starts to shrink. Nevertheless, we have seen, good, sizable throughput improvements when you turn on hardware offload feature on OVS with this. Okay, so I talked about the partial offload, so here's a good pictorial view of that. So you would be basically using the NIC to help you accelerate the flow lookup. You're still responsible, you being the vSwitch software here, responsible from the action resolution and then related I/O. Say, for example, if you're trying to make that packet up all the way from the physical function to the virtual port of that application endpoint, it could be a VM container, whatever, then you're responsible from driving that as part of your software. But the good thing is you can see the packets. I mean, you can still see, look at the packets, count them, do whatever you want to, do statistics-wise. So in the case of full offload to the right, here, the virtual ports of that endpoint is really backed by the NIC hardware itself. So in the ideal case, you figure out all these rules and install it into the NIC, and then you don't see anything else after that point, right? So, which is great. But if you need to do anything about those flows, you really need to go down to that hardware and see what's happening with those flows. So these are the partial and full offload notions that was referenced earlier. And what's important here are 2 things. One is when you take a flow and install it into that hardware, what's the performance? How much upside are you seeing in terms of, especially in the case of partial, you're still going to need to reference those flow data structures. So if you're trying to save from bringing those flow cache lines into your CPU, maybe it's not going to save you much, but it certainly will save you CPU cycles in terms of, doing that pre-processing. So, and also capacity, right? So maybe more on this in the coming slide. So assuming we will have unlimited offload performance and unlimited flow capacity is not realistic. So that reminds me of the famous, triangle of truth. So you can probably have 1 or 2 of those edges, but not 3 of them at the same time. So then how can you take the partial or the full offload case and turn it into a graceful one, right? So it will be probably a responsibility shared between the application, the API itself, and maybe some of the other auxiliary libraries that might help this turning into a graceful one. So one discussion is probably is a classical one, but it's very relevant as to which flows belong to which of these paths. So there's this fast path and a slow path, and the only thing this reminds me is actually CPU cache management, along with its 20+ years of legacy research on it, right? So same thing here. So if you are to offload this thing, first of all, you're going to place it. So even if you had the space, is it really worth putting it in there? Because like I mentioned, there's some cost associated to it. So if you received a packet, resolve the flow, and just put it right down there blindly, and you will only see 2 more packets belonging to that flow later on, was that worth it? The CPU cycles you spent for actually offloading it probably was, good enough to process those remaining 2 packets, right? So, and I know actually for some commercial deployments, people have chosen to hold on to installing rules until they've seen certain amount of packets on a given flow. So another one is replacement. At some point, if you run out of space, what do you do now? So the case for OVS currently is it will basically go through all these flows that could be installed, it will install them, and done. So in the case where I was trying 10,000 flows on a hardware that supported 7 or 8K entries, those remaining 2K entries will get, hardware errors for installing those flows. And it's not going to, magically evict some of those flows out thinking that, oh, this new one might be more important. So he wouldn't know. So that's kind of like the application's responsibility. So, and we did live in a world where we have developed a lot of cache replacement algorithms for CPU caches, like LRUs, NRUs, random ones, FIFOs, et cetera. So are they applicable? So aging is another one, right? So if you don't do anything, you will run out of space. If you age things, it might be good, but how do you age things and where? So the current behavior with this particular application we looked at, things will age out at a handful of seconds, probably like 10 seconds by default. So only after that 10 second, you will start actually deleting those flows from your caches, or invalidate them, and then go to your hardware and remove them. But even if you have a kilobit per second kind of like flows, you will see them in that time. So they will never time out, right? So how do you adjust that timeout? Where do you age it? Do you have an independent but somewhat coordinated aging mechanisms in your hardware as well as your software part? So another good one is about compute memory trade-off. So as you noted, there was some ability for you to put wildcards into your rules, right? So say, for example, you installed a rule to your hardware at a certain point in time and you've seen a packet, and then later on you've seen another packet, then there was another rule, and then there was a way for you to combine those. So is it worth to really take that computation and now delete that flow that was down there and put a wildcard rule that would cover both of them if their actions were compatible, say, for example? So, or can you craft this whole software infrastructure such that you don't really try to go very precise with your rules, but have maybe like coarse rules that will later help you more in software, so you have a cross-optimization between the hardware offload and the software. And we all know that not all flows are created equal. We all know that, but how do you really tell when the rubber hits the road, right? So what is available for you to really count them? So, and then there are short-lived flows, long-lived ones, bursty ones, elephants and mices of the world. So there are some libraries that are very useful in constructing a graceful offload scheme for your software. So RTE hash is a hash library that is really good and suitable for creating flow caches. So very efficient data structures are there. And RTE member is a membership library that lets you easily test whether something that you have received and are looking to see whether it was present in a group that you already defined. It's kind of like a counting, or it's kind of like a Bloom filter membership situation. And RT table and RT flow classify APIs give you good means to create a flow table where you have rules that you can match against those. So these are components that are useful, and some of the future components that we are interested in, you've heard about, a relevant one earlier in the talk, but we're working on something called, a heavy hitter detection. We're trying to understand whether we can come up with, a probabilistic data structure that doesn't require you to count every single packet to understand the flow statistics, but, be a little bit more intelligent in terms of how you sample and still get some statistics about the flows. The importance of that is if you're able to say that, oh, this particular flow is actually volume-wise covering a lot of my traffic, then those would be the guys that might be sticking to your hardware a lot more than these others who might be actually coming and going, right? So you can somewhat create some preference for certain flow rules by using libraries given to you. So it is a lot simpler if you were to do this in a partial offload setting, because you will still be seeing those flows in the software, so you can use those libraries. In the hardware case, you will probably require some hardware assistance to get statistics information from the hardware. So we've seen a nice way in the earlier talk, so maybe there will be good APIs for us to use those as well. So with that, I just would like to conclude and thank you for your time. There are some references out there that you can check out, and here's my acknowledgements. And if you have any questions above and beyond what you might squeeze in here today, feel free to send an email. Thank you.
Maybe we take just one question?
Sure. What are the next offload that you're planning to implement? For example, you can have count, which should solve some of the problems, or something like that.
It's really tricky to understand. Can you repeat that?
Sure. You said that you currently support RSS and mark action. what is the future plan? What do you plan to support more? Are there more actions that you're planning on to support?
Oh, you mean as far as the I4T
flow,
driver
yes.
goes? That would be probably a good question for our software execution team. I'm not really aware of their execution plans as to what might be coming up. But I think it's somewhat related to the applications. As more applications show up with these actions, I mean, it's all out there. So I think I've seen a lot of actions in the RT Flow API documentation that were more recently added. I don't know which ones are supported in our particular hardware or the ones that are coming up. But it would be probably interesting to see which applications do make use of, say, for example, in the OVS case, this is how it naturally happened, right? So OVS started to make use of this, and then we basically, made the legwork to enable it. So.
Great. Thank you.
Sure.
Thanks.